In this video, we want to discuss the application of using Laplace to analyze circuits. I'll talk a little bit about replacement of circuit elements with elements in the Laplace domain, and then hopefully in this video have time to work one example. If not, work an example in the follow-on video. So the goal when using Laplace analysis in circuits is to realize that elements including capacitors and inductors introduce differential elements into our circuits equation. So we know that V is L di dt for an inductor. We know that C dV dt is what we would replace for a capacitor in our equations, and so we end up having differential equations. We're going to take advantage of the fact that the Laplace method can be used to solve differential equations. So one option would be that we wrote normal node and mesh equations, inserting the differential elements for the derivatives for currents and voltages, for capacitors and inductors, and then solve the differential equation. But it turns out, instead of doing that, it's much easier to work with the circuit itself and transform the circuit into the S domain, solve the circuit in the S domain, and then take the inverse transform to get a solution. So basically, when we solve circuits using Laplace, we have a three-step procedure. So the first thing we do is we write down the time equation that relates the terminal voltage to the terminal current. Then we Laplace transform that time domain equation to generate an algebraic relation between the S domain current and voltage, and then finally we construct a circuit model that satisfies the relationships between the S domain current and voltage. And so this is done in an actual circuit. This is going to be done element by element. Once you get used to doing this, then the substitution becomes automatic. So let's look at the different elements. So first of all, resistors, when they transform, the only thing that really changes is, you note on the left we have a time domain voltage and current. On the right we'll have a Laplace domain or S domain. So voltage and currents that are functions of time are going to transform into voltage and currents that are functions of S. The resistor, because the relationship is Ohm's law, V is equal to IR, when we transform that equation, we just get V as a function of S is equal to I as a function of S times R, which was a constant. So basically, resistors remain the same in the transformed circuit. Inductors, V is equal to L di dt, and an inductor is capable of having an initial condition current. So our I sub 0 here is our initial current through this inductor, and I want you to note that we have two terminals, A and B, and the voltage in the time domain is going to be defined across the inductor from terminal A to terminal B. The current will flow into the positive terminal of the voltage following the passive sign convention, and it will flow from A to B. As long as in the circuit it's set up this way, then V is equal to L di dt. When we transform this equation, so first I want you to focus just on this equation. And if we apply the derivative property, then basically the voltage, which is a function of time, will transform into a voltage which is a function of S. The di dt, using the derivative property, becomes S times I minus the initial condition I at 0 minus. So when we combine that and multiply it by L, we get this SLI minus LI naught. So notice here we have a relationship that ties voltage directly to current. This is very similar to finding that V is equal to J omega L times I in the phasor domain, except here we're in the Laplace domain. So the multiplier here, which is going to become what we call our impedance, is S times L. So basically, when we replace the inductor with an inductive impedance, its value becomes SL. The current now becomes I of S. The voltage becomes V of S. And notice that the voltage is going to be between the terminal A and B, but we have this other term, this minus Li0. Now, because this is a voltage equation and voltages add in series, in the circuit we can model that as a voltage source, because remember, I0 is a constant. And notice that it's negative, so if we're going from A to B, the drop across the inductive impedance is ISL, but the drop across the voltage source is minus Li0. So this is the equation that would model the voltage drop across the inductor. Just be careful to note that it is the voltage drop from terminal A and B. So that's important if you're trying to find a voltage and then work back to the time domain. If you're trying to find the voltage from A to B in the time domain, you have to be sure that in the Laplace domain you find the entire voltage, which is going to include this little source in series. Now, a lot of times with inductors, it's easier to do a source transformation at this point, and then we model it as an inductive impedance in parallel with a current source. And the nice thing about this is if you do this, the direction of the current source is in the same direction as the current in the original time domain circuit. So the current source obviously is proportional to this I sub 0. When you do the source transformation, you end up with I sub 0 over S. Nice thing about that is, if you remember, 1 over S transforms back to a step function. So in this model, this basically just looks like a step function current source that's been transformed into the Laplace domain, and so the element becomes a current source, current I0 over S. The voltage is now a simple voltage from terminal to A, from A to B, across the inductive impedance. I don't have to compensate on the voltage with this series voltage source. So in my opinion, it's always a little bit easier to model the inductors as an inductance in parallel with a current source. Of course, it depends on the circuit. The capacitor, we have the same thing we have in the time domain. The capacitor, we have the equation I is C dV dt that gives us the current voltage relationship. The voltage drop from A to B is modeled as V of t. The current flowing from A to B is modeled as I of t. The voltage, the initial condition on the capacitor voltage is V0. So if we transform this equation into the Laplace domain, we end up with the following equation. I becomes a function of S. We have SCV minus CV0. So if we then try to model the capacitive impedance, we end up with 1 over SC. So let's think about that. The equation I is equal to something times V, this would be an admittance. We don't talk about admittance much, but it is 1 over impedance. So in an impedance type relationship, we would have I is equal to an impedance, or we would have V is equal to an impedance times a current. If we flip that, V is 1 over an impedance times, or I is 1 over an impedance times a voltage. Sorry, I keep saying that backwards. So basically the impedance here would be, if we move this 1 over SC over here, so the impedance of a capacitor in the Laplace domain, the equivalent impedance is 1 over SC. And then because this is a current equation and we have the algebraic sum of currents, we'd end up with a current source equal to C times V0. Now once again, it's most common in a capacitor to represent that, take a source transformation and represent that as an impedance in series with the voltage source. Doing the source transformation, the voltage source becomes V0 over S, which is a Laplace domain representation of a DC voltage source that turns on at t equals 0. The capacitor becomes a capacitive impedance having a value of 1 over SC. So inductors and capacitors in the Laplace domain both become functions of S And when we do the substitution of the element, we're basically taking this circuit shown here and we're substituting it for the time domain circuit, so that we're going to be able to write node and mesh equations, voltage divider equations, whatever, directly from the Laplace domain equivalent circuit instead of taking a time domain circuit and trying to do a differential equation. So figure 13.6 illustrates what to do with the capacitor in the time domain. So I think I have a summary chart. Yeah, so this is a very handy chart included in your notes. It shows how you have the time domain on the left, you have the frequency domain on the right. Okay, let me comment about frequency domain. This is not frequency domain j omega. The frequency S is a complex frequency, which means it includes transient effects. So really, if I were writing this textbook, I would use this language, S domain, because it is Laplace domain. But S technically is a complex frequency, so it's okay to say it's frequency domain. I might say complex frequency domain. The more common substitution for an inductor is the substitution on the right, where we substitute an inductor in parallel with a current source. Reason for that is maintenance of the direction of the current source with the original direction in the circuit, so there's no confusion there. Also, ease of finding a voltage because you maintain the same terminal pair voltage. In a capacitor, we normally will substitute the capacitor in series with a voltage source. Once again, the voltage source maintains the same kind of polarity that it did in the circuit in the time domain, so that makes it easy not to have to worry about direction. Okay, I think I might want to do one or two more slides. All right, so now you've seen basically how to transform inductors and capacitors from a time domain circuit to a Laplace domain circuit. And what I want to talk about here is I just want to give you an overview of the method that's going to be used for solving circuits. So the first thing that you have to do before you can do anything else is you have to determine the initial condition for all of the inductors and capacitors in your circuit. This usually involves solving the circuit at t equals 0 minus, assuming everything's been hooked up for a very long time, and getting a condition on the L's and the C's before you transform the circuit. Because remember, our transformation, if you look at this table, remember we have these initial conditions present. So it's important to know what the initial conditions are. You then do a Laplace transform of independent voltage and current functions. If we have DC, the DC source is going to be modeled like a constant times a step function. When we transform it, we have to transform that. When you have like unknowns, I1, I2, I3 in the time domain, those become I1, I2, I3 in the Laplace domain. So all of the current and voltage functions would have to be transformed into S domain symbols. So that would be step 3. You then transform the remaining circuit components, so that would be the inductors and the capacitors, into their S domain equivalent. And then at this point, you just do a normal analysis of the S domain circuit. Now, step number 6, I've never really utilized, but it is possible when you get to this point and you get expressions for currents and voltages in the Laplace domain, it is possible to use initial value and final value theorem to be sure that your voltages and currents in your S domain have initial and final values that are consistent with what you would expect in the circuit. Once again, this is a step that I never really use, I guess because I'm confident enough in my transformation, although probably, to be honest, I use it without really thinking about it. So I think I probably do this subconsciously in my head, look to make sure it makes sense and there's nothing weird. Obviously, if you're analyzing a real circuit, you also want to make sure that you don't have any undefined functions or singularities or things that are going to transform back into impulse functions or their derivatives, because it's unlikely that you would get something like that in a circuit. You're typically not going to get hyperbolic sine and cosine unless you've got a source that contains that. So typically, when you get a function in the S domain, it'll be a polynomial. The denominator of the polynomial will be of higher order than the numerator, and the solutions will either be exponential decay, a polynomial in time like a ramp, or sinusoidal or step functions. So if you're looking at your Laplace function and it doesn't look like it's going to produce those, or it'll be something that looks like the source. So if the source is sinusoidal, you'll have some sinusoidal looking terms in the Laplace domain. Okay, and then finally, once you have that equation, you inverse transform the S domain voltages and currents using partial fraction expansion. So this textbook is going to repeatedly refer to this as analysis method 13.1. It's just the Laplace analysis method. And so we're going to do several examples that illustrate how this works in upcoming videos. This will be the first one that we do.